Maxwell's equations are not four random formulas. They are a mathematical language for describing fields. A field assigns a value to every point in space. Instead of tracking every particle individually, mathematics lets us describe the entire space using functions, vectors, derivatives, and integrals. An electric field is written as a vector, usually called E. A vector has both size and direction. So, at every point in space, the electric field tells us two things: how strong the field is and which direction a positive charge would be pushed. A magnetic field is also a vector, usually called B. This gives Maxwell two major mathematical objects, the electric field E and the magnetic field B. The equations do not describe only one location. They describe how these vectors vary across space and through time. The first important mathematical idea is divergence. Divergence measures whether a vector field is spreading outward from a point or gathering inward. Imagine placing a tiny mathematical box inside a field. Divergence compares how much field leaves the box with how much enters it. Gauss's law for electricity says that the divergence of E is related to charge density. In simple form, it is written as divergence of E equals charge density divided by epsilon naught. This means electric charge acts as a source or sink of the electric field. The same law can also be written using an integral. Instead of examining one tiny point, we surround a volume with a closed surface and measure the total electric field passing through it. The integral form and differential form describe the same rule at different mathematical scales. The second equation says the divergence of the magnetic field is zero. Mathematically, this is written as divergence of B equals zero, means magnetic field lines do not begin or end at isolated points. The equation describes a field with no magnetic sources or sinks. The next mathematical idea is curl. Curl measures how much a vector field circulates around a point. Imagine placing a tiny paddle wheel in the field. If the field makes the wheel spin, the field has curl. Curl is a local measurement of rotation. Faraday's law connects curl with change over time. The curl of the electric field equals the negative time derivative of the magnetic field. The negative sign is important. It represents opposition. The induced electric field acts in a direction that resists the change producing it. The fourth equation connects the curl of the magnetic field to electric current and changing electric fields. In mathematical form, it includes the current density term and the time derivative of E. Maxwell's correction was the extra changing electric field term, which made the equations mathematically consistent. Notice the structure of the equations. 2 use divergence, which describes sources and sinks. 2 use curl, which describes circulation. This is not accidental. Maxwell's system separates the behavior of fields into 2 basic mathematical questions. Where does the field spread, and where does it rotate? The equations also use partial derivatives because the fields depend on several variables. The electric field can change with position, time, or both. Partial derivatives allow us to measure one kind of change while holding the other variables fixed. This is how calculus describes a field evolving through 4-dimensional spacetime. The symbols epsilon naught and mu naught are constants. Epsilon naught describes how electric effects behave in empty space, while mu naught describes magnetic behavior. Their product determines the speed of electromagnetic waves. Maxwell found that this speed matched the measured speed of light. When Maxwell's equations are combined, the result becomes a wave equation. The electric field satisfies a second-order differential equation involving changes in space and changes in time. The magnetic field satisfies a similar equation. The mathematics predicts waves even before we discuss light or radio. The wave equation has a familiar mathematical form. The second spatial derivative is connected to the second time derivative. This same pattern appears in vibrating strings, sound waves, and many other systems. Maxwell showed that electric and magnetic fields follow this powerful mathematical structure. That is the deeper achievement of Maxwell's work. 4 compact equations use vectors, divergence, curl, partial derivatives, integrals, and constants to describe an enormous range of behavior. The physics is important, but the mathematics is what unifies everything. A small, elegant system can explain waves, fields, communication, and light. Subscribe to Math Animated for more clear, visual educational videos like this.